This is lesson 3 in our Calculus 3 series, the dot product. So far we've talked about adding vectors and multiplying a vector by a scalar. But what would it mean to multiply vectors? Is there a way that we can multiply vectors and get something useful? Well, the answer to that is yes. There's two ways we can do that, and in this section we'll be talking about the first way, the dot product. So for vectors a and b, we're going to have a dot b to be a1b1 plus a2b2 plus a3b3. Now the first thing I want to point out here is that this is a scalar quantity. We are multiplying two vectors and we're getting out a scalar. We can also define the dot product in R2, and a dot b would be a1b1 plus a2b2. And we'll see how this ties into what we've already seen with the length of a vector and how else this can be useful geometrically. But first, let's take a look at a couple of examples. If a is 3, -1, 0, and b is 4, 2, -3, then let's find a dot b. It's going to be 3 times 4 plus -1 times 2 plus 0 times -3. And so we're going to get 12 minus 2 plus 0, and so that value is equal to 10. And again, we'll see in a little bit what this tells us geometrically, but for now, we'll leave it at that. Now let's take a look at some of the properties of dot product based on the definition. First one we'll look at, a dot a is the length of a squared. Well, here we're talking about a1, a2, a3. So let's take a look at a dot a. By definition of dot product, it's going to be a1 times a1, or a1 squared, plus a2 times a2, plus a3 times a3. So we've got a1 squared plus a2 squared plus a3 squared. And we know that the length of a is given by a1 squared plus a2 squared plus a3 squared under a radical, so this in fact is the length of a quantity squared. Let's take a look now and show that a dot b is equal to b dot a. A dot b, by definition, is a1 b1 plus a2 b2 plus a3 b3, and of course, by commutativity of multiplication, this is b1 a1 plus b2 a2 plus b3 a3, which is b dot a. Next we have a dot b plus c. We've got a distributive property of the dot product. This is going to equal a dot b plus a dot c. So again, we'll start with the left-hand side, and here c, as you might guess, is c1, c2, c3. Then b plus c is going to be b1 plus c1, b2 plus c2, b3 plus c3. And so a dot b plus c, by definition of dot product, is going to be a1 times b1 plus c1 plus a2 times b2 plus c2 plus a3 times b3 plus c3. And of course, this is a1 b1 plus a1 c1 plus a2 b2 plus a2 c2 plus a3 b3 plus a3 c3. And just reordering the terms, we have a1 b1 plus a2 b2 plus a3 b3 plus a1 c1 plus a2 c2 plus a3 c3. I'm just reordering the terms here, and this we know is a dot B, and this we know is A dot C. And so we have proven that property. The next property deals with scalar multiplication with a dot product. So we note that C times A, where C is a scalar, A is a vector, dotted with B is the same as C multiplied by A dot B, which is the same as A dotted with C multiplied by B. So keep in mind here that now C is a scalar in this property. Here we had C as a vector, and that was clearly noted with the vector hat. Now here we're talking about C being a scalar. And so let's just take a minute and just recognize that these multiplications are well defined. So this is a scalar multiplying by a vector, so we're going to get a vector, and a vector dot a vector. So this total quantity is going to be a scalar. And here we've got a vector dot a vector, so that's going to give us a scalar, and then we have scalar times scalar, so that's still a scalar quantity. And here we have a vector dotted with this, which gives us a vector, so vector dot vector is still a scalar. So it's good when you've got scalars and vectors and multiplication going on to just pay attention to the notation and make sure you understand what kind of quantity you're talking about. So let's start with what we have here. C times vector A is going to be CA1, CA2, CA3. And for this last part, we're going to need C times vector B, so let's write that one down as well. CB1, CB2, CB3. And now we'll start with the left-hand side. CA dot B is going to look like CA1, B1 plus CA2, B2 plus CA3, B3. Now if we factor out the C, we notice that this is C times A dot B. And we've proven the first equal sign. Right? We've got from here to here. To prove this second equal sign, let's go back to having it all distributed here, and then let's recollect it in a different way. So from here, we can go A1 times CB1 plus A2 times CB2 plus A3 times CB3, and then we can recognize this as A dot CB. And that's what we needed for that second equal sign here. And we've proven this property as well. Just one more property we want to prove. The zero vector dotted with any vector is going to be 0. And again, just pay attention here. This is the zero vector, and this is just 0, scalar. So 0 dot A is going to be 0 A1 plus 0 A2 plus 0 A3, and that is definitely going to give us 0. Now let's take a look at the geometric interpretation of the dot product, and this uses the law of cosines. Just as a reminder, the law of cosine says side c squared of a triangle is equal to a squared plus b squared minus 2ab cosine angle C, or in this case I called it theta. Okay, so let's take a look at, in three-dimensional space, we've got some vectors here. We've got vector A, vector B, theta is the angle between them, and then let's complete this triangle, and what vector is this that would complete this triangle? Well, we can think of it this way. We know that when we put vectors tail to tip, we're adding them together. So B plus what vector is going to give us vector A? that would have to be vector a minus b. Right, so this is vector a minus b, whose length makes the other side of this triangle. So let's apply the law of cosines to what we have here. Our c squared that we have in this picture is the side length here, so that's going to be the length of a minus b quantity squared. And that's equal to a squared plus b squared, so that gives us the length of a square plus the length of b square minus 2 times the length of a times the length of b times cosine of the angle between a and b, cosine of theta. Okay? Let's see how we can simplify this. Remember from our properties of dot product above, we showed that a dot a is equal to the length of a quantity squared. So here, what we have is really a minus b dotted with a minus b. And here we have a dot a. Here we have, I keep forgetting my b hats. Here we have b dot b minus 2. I'm going to leave these in here. Let's simplify some more. By the distributive property we showed above, we can essentially FOIL this out with our dot product. So we're going to have a dot a minus a dot b minus b dot a, and then plus b dot b. And that's our left-hand side. Still here we have a dot a plus b dot b minus 2 length of a, length of b, cosine theta. And we can cancel additively here. And notice that these a dot b and b dot a, those are the same. So this is negative 2a dot b is equal to negative 2 length of a, length of b, cosine theta. Simplifying further, we have a dot b is equal to length of a, length of b, cosine of the angle between them. And this is going to be a very important formula for us, so you will definitely want to remember it. And we'll do lots of practice with it as well. Keep in mind with this, when we're talking about angle theta, we're talking about the angle between the two vectors, the angle that is between 0 and pi. So we could essentially take the long way around and talk about that angle, but we're not going to do that. So the theta that we're talking about here is always going to be between 0 and pi. Now let's take a look at this problem. If a vector A is 2, 0, negative 2, and vector B is 0, negative 2, 4, find the angle between A and B. Well, we know that we're going to use this formula here. A dot B is length of A, length of B times cosine theta. So A dot B is 2 times 0 plus 0 times negative 2 plus negative 2 times 4, and that gives us negative 8. Magnitude of A is square root of 2 square plus 0 square plus negative 2 square. So that gives us radical 8, 2 radical 2. Length of B, 0 square plus negative 2 square plus 4 square. That's radical 20, or 2 radical 5. So we know that A dot B is equal to length of A, length of B, cosine of angle theta. So cosine of angle theta is going to be a dot b negative 8 over length of A, length of B. So that's going to be 4 radical 10. And that's negative radical 10 over 5. So theta is then cosine inverse of negative radical 10 over 5, which is approximately 2.26, and remember that's in radians, or if you wanted to have an idea of what that looked like in degrees, it's about 129 degrees. Let's take a look at the sketch in three-dimensional space so we could see how this all comes together. Vector A is 2, 0, negative 2, so we're coming out 2 units in x and down 2 units in z. And then vector B is 0, negative 2, 4, so we're not moving in the x direction, we go 2 to the left in the y and 4 up. And then this is theta, the angle between them, which is about 129 degrees. Now we're going to talk about orthogonal vectors. Non-zero vectors A and B are said to be orthogonal or perpendicular if the angle between them is pi over 2. Now we know that cosine theta is equal to A dot B divided by length of A times length of B, and we know that this theta is between 0 and pi. So if A and B are orthogonal, then what information do we get from this equation? We know that cosine theta is cosine pi over 2, which is 0. So 0 is going to equal A dot B over length of A, length of B. This tells us that A dot B must equal 0. So if A and B are orthogonal, then their dot product is equal to 0. We can take a look at the converse of that statement as well. If A dot B is equal to 0, then we know that cosine theta is equal to 0, and theta is between 0 and pi. Therefore, theta must be pi over 2, and that says A and B are orthogonal. So if A dot B is equal to 0, then A and B are orthogonal. If A and B are orthogonal, then A dot B is equal to 0. So we have an if and only if statement here. A and B are orthogonal if and only if A dot B is equal to 0. Also very important, you will want to remember that. For example, find a vector orthogonal to 2y minus 3j plus k. Find a vector. Okay, I'm going to call that vector v, and that's going to be v1, v2, v3. And I'm going to write the component notation here for this vector. This is 2, negative 3, 1. Find a vector orthogonal to 2, negative 3, 1. My vector is v1, v2, v3. What do I need to be true about this vector? I need the dot product to be equal to 0. So we need 2v1 minus 3v2 plus v3 to be equal to 0. So if we let v1 equal 1 and v2 equal 1, then that's going to give us a negative 1. So we can let v3 also equal 1. And then we'll have 2 minus 3 plus 1 is equal to 0. So our vector v we can choose is 1, 1, 1. Nice and simple. There are going to be infinitely many vectors that are orthogonal to this given vector. This is just one of them. We're going to see in the next few lessons that there's going to be a whole plane full of vectors that are orthogonal to a given non-zero vector. We have one more topic in this lesson, and that's projections. And this type of thing comes up often when we're talking about forces. For example, if we have an object here on the ground that we want to move in direction of vector A, but for convenience we're pulling it up in direction of vector B, we're interested in how much force is actually going in that direction. We want to know what component of vector B is actually in the direction of A. So the first thing we're going to do is take a look at the projection of vector B onto vector A and take a look at that length. Now I like to think of the projections as being like a shadow. If the sun is shining perpendicular to vector A, what would the shadow of vector B be? It would be this length here, right? And so what is that length? Well, if the angle between the two vectors is theta, then this length is going to be the length of vector B multiplied by cosine theta. And we can write cosine theta as A dot B over length of A, length of B, so that this length then becomes A dot B over length of A. And we're going to call this the component of B along A. And we denote that by comp of B, and we have a subscript here of vector A. Well, now we have the length of the projection of B onto A, but we'd like to be able to represent that as a vector. So we want a vector in the direction of vector A, but with this length. So what we want to do is take a unit vector in the direction of vector A and multiply it by this length. Vector projection of B onto A has length component of B along A and is in direction of vector A. So we take a unit vector in direction of vector A, so that's going to be A over its length, and scale it by the component of B along A. So I'm scaling it by this, and then just simplifying looks like this. Remember that A dot B, these are vectors, so this is a scalar, and this is scalar multiplication of A, and then divided by the length of A squared. And that's the projection vector of B onto A. That's vector projection. In lesson 1, we found the distance from the point 3, negative 1, 2 to the x-axis by recognizing that the point on the x-axis closest to this point was 3, 0, 0, and we took the distance between those 2 points. But vector projections gives us another way in which we can solve this problem. So let's take a look at a vector with terminal point 3, negative 1, 2. We can think about projecting onto vector I, which is a unit vector, remember, in the direction of the positive x-axis. If we project our vector onto the x-axis or onto vector I, that'll give us this green projection vector, but that's not going to give us the distance that we want. The distance that we want is this length here. So we can consider the vector that is formed here by the subtraction of these two vectors and take its length. That's going to give us the distance that we want. And yes, it's a little bit of a longer way than we did in lesson 1, but this is going to generalize for us. The method that we had in lesson 1 by just recognizing the closest point isn't going to work for us in general. So let's take a look at the computation here. We have vector B being 3, negative 1, 2. It's the vector that takes us to this terminal point here. Vector A, on which we're going to take the projection, is going to be I, our standard basis vector, in the direction of the positive x-axis, so that's 1, 0, 0. And then what we need for this distance here, that's going to be the length of B minus the green projection vector. That's the distance that we're looking for. So let's make this computation. Projection of B onto A is given by the formula A dot B multiplied by vector A over the length of vector A squared. And that, in this case, A dot B is just going to be 3. And then A is the vector I, so we have 3I over. Now vector A is a unit vector, so its length is 1. So we have 3I over 1, or just 3I, or the vector 3, 0, 0. And we knew that already, right? That vector was going to be 3, 0, 0. And now let's subtract b minus this projection vector. So we're taking 3, negative 1, 2, subtract 3, 0, 0, and so we're left with 0, negative 1, 2. 0, negative 1, 2. We're moving 1 in the negative y direction and 2 units up, so that looks right. And then finding the length of that vector, we get radical 5, and that's the same distance we found in lesson 1. And in general, this vector, b minus the projection of b onto a, has its own name. It's the orthogonal projection of b onto a, because as you might guess, that comes up often as well. So let's just write that down, subscript a, and that's equal to b minus the projection of b onto a. And we'll conclude our lesson for the dot product here.